Hello everyone. In this tutoring video, I go over the proof of the derivative of Euler's number raised to the power of x, and how this special derivative can be used to solve first-order differential equations. Using the formal definition of the limit discussed in the last video, we can use the basic algebraic identity of exponents to rewrite e raised to the power of x plus h equals raised to the power of x times e raised to the power of h. So we can rewrite this as e to the power of x times e to the power of h minus 1. And since we are differentiating with respect to h, we can get rid of e to the power of x and treat it as a constant, i.e. 1. So the limit now becomes e to the power of h minus 1 over h. We now use substitution, substituting eh minus 1 for y, and also noting that eh minus 1 as h approaches 0 is 0 because e raised to the power of 0 is 1 and 1 minus 1 is 0. We can now notice, if we isolate the function by itself, eh, it will equal the substituted value y plus 1. This may seem useless at first, but we can use this to take logarithms of both sides, which is the next step in the proof. We can now simplify the left-hand side to simply be h, and we can go back to the derivative and rewrite it in terms of the substitution y. Doing this gives y in the numerator and ln of y plus 1 in the denominator. We can now rewrite this further by taking the reciprocal of y. So the numerator becomes 1, and the denominator gains the term 1 over y. And using an identity from logarithms, we can now remove the 1 over y term and raise the logarithm by 1 over y. We can now notice that Euler's number is defined as the limit of, as x approaches 0, the function of x plus 1 raised to the power of 1 over x, which is exactly the function we have in the denominator. Therefore, the denominator becomes ln of e, which by definition of the natural logarithm is 1, so the limit is 1 divided by 1, which is still 1. However, we are not quite done yet, as we have to put this in terms of the original derivative. So since we have proven that e raised to the power of h minus 1, all of that divided by h equals 1, we can remember by one of the algebraic rules of exponents that the function can be rewritten as e to the power of x times that limit, which means that e to the power of x times 1 equals e to the power of x. Therefore, the derivative of e to the power of x is itself. This property is useful for solving first-order differential equations, because now we have an exact solution where the derivative and the function are equal, which is what a first-order differential equation asks, just like a second-order differential equation asks about the second derivative being equal to the function. First-order differential equations are used in some subfields of physics, most noticeably the relationship between displacement and velocity in mechanics, Newton's law of convective cooling with thermodynamics, and the relationship over time with voltage and capacitance, or current and inductance in the study of electronics and electrical engineering.